what we have seen so far is when we started with the mathematical formulation of method of moments, the first example we took was the surface integral formulation. The second example is going to be related complementary method, which is called volume integral. Okay. So, I'll explain when one is needed and when the other is needed. Okay. So, let's sort of start by summarizing what we already know. Okay, what have we already solved? So, what we have, I am going to draw our favorite diagram once again. Right, this was our V1, this is our V2, and some current source over here J. Right, that is our problem. I had called this S infinity, and this was S. Okay. So, what kind of equations did we write for these two regions? They were the wave equation, right. So, after I simplified everything, I had something like in either region, and where did the current source appear? There was a current source J over here. In these equations, where did the current source find an appearance? Which of the terms contains the current source? F of r, right. So, f of r was something like actually j omega mu j of r, right. So, we just absorbed it into f of r. So, this equation we have seen it many times by now. We will call this it's like the Helmholtz equation, and then we said, okay, how do we solve this? So, to solve this, we said we invented one new function, we called it the Green's function, right. So, I said okay, if I can find out this Green's function, I can solve this problem, right, and that was the impulse response idea. But notice one thing that was required in both of these equations is that the operator that I have on the left hand side, that for both the equations is the same, right, and that operator is what? It's like del squared plus k squared. When the operator is the same, I can use the Green's function. Okay. Now, when we went to actually solve for this Green's function, what did we do? The steps briefly. We converted it first to 2D polar coordinates. I wrote down the Laplacian in the polar coordinates, and after some amount of algebraic manipulation, what did I end up with? I ended up with a differential equation, right. So, and that differential equation looked like a well known differential equation, which is Bessel's differential equation, right. So, when I went to solve this, I got something that looked like x squared y double prime plus x y prime plus x square minus alpha squared y is equal to 0, right. That was what I called differential equation. Right. So far so good, and in our case turned out alpha was what? 0. Alpha was 0. That is why our solutions were Hankel 01 and Hankel 02. Okay. So far this is just a revision. Now, this equation over here, let us call this equation 3 and equation 2, right. Equation 3 did not have any k term over here, correct. There is only x, y and alpha, which is 0, but our original equation 2 had a k. So, we had to do one more manipulation, and that was x equal to kr, right. So, I had the substitution that kr is equal to x, right? The x was absorbed into it. What is implicit over here was k is a constant, right. So, that is why I could do this substitution easily. It was a very simple change of variables, right. So, here what we did without really being very explicit about it is that k is a constant, right. So, if I ask you what is the physical meaning of k, so there is some value of k over here, we called it k1, and some value of k over here, I called it k2. For this approach to work, what must be true about k? We have seen that to get Bessel's solution out of this, it should be a constant, right. So, k1 let us say vacuum, k2 whatever material, But implicit, because I want the same solution strategy to work, is that k should be constant. Therefore, this in what we have done so far, everywhere over here in this region k2 is constant. So what kind of an object is that? Homogeneous object, right? So it's a now real life objects, will they always be homogeneous? Obviously not, right? Think that you are calculating the RCS of some aircraft over here, right? This is some aircraft. Okay, there's some cockpit over here, so you'll have some glass over here, some metal over here, right? Different components are there. So this is all realistic objects are going to be heterogeneous. So can I apply this approach that I've discovered so far, this surface integral approach? Can I use it to this kind of a problem? Well, the answer is yes and no. Yes, if I can break it up into small sub-regions, each of which is constant k. So I can say, okay, so I can take all the metal parts and say, okay, this is, so instead of volume 1 and 2, I may have volume 1, 2, 3, 4 up to n. Then I'll have so many different surface integrals. Each of those I will have to put boundary conditions and solve it. Okay, that is one approach. But that will break down if, for example, my material has some continuous variation in refractive index, permittivity, whatever you want to call it, right? So if an object is truly heterogeneous, then this approach, you can see it's doomed to fail. Okay, that's where this other approach comes, which is volume integral. So as the word suggests, surface integral formulates the equations around the surface. Volume integral goes into the volume and solves it. So advantage is I can model more difficult objects which have heterogeneity. And what do you think would the disadvantage be, or the downside? More computation, because well, we'll talk about Green's function. The computations, number of computations, as I take a surface area, will have more number of elements to calculate than just the line around it, right? So computation is going to increase, but that's a price that I have to pay for solving this. So there's a question about what about Green's function?
Don't we have 3D Green's function?
Right. So we have a Green's function that we are using over here for the surface integral formulation. We are going to continue to assume that it's a 2D problem that we are solving. So we are not going to 3D. Okay. So our difficulty is we do not know in closed form Green's function for a heterogeneous medium. That is our problem. I am not saying it's not possible to find it. There will not be a closed form solution, there will be a numerical solution. Okay. So we want to avoid that as much as possible and use what we already know. And what we already know is a homogeneous Green's function. So the question is, can I still use that somehow and get some accurate way of calculating it? Okay. So we will use the Green's function, but how to get to it is going to be a little bit tricky. So we will see how to do it. Okay. So how our current problem is different, as I have already said, that epsilon r is actually a function of space, okay, within V2, right. So this is a V2. So within V2, this is varying as a function of xy. Okay. So now how do we continue to use our approach over here? So let's use what we already know. Okay. So what we already know is the wave equation, right. So let's say when there is no object. Okay, so I have the current source over here and there is no object over here. So what will my Helmholtz equation be? So I'll have a del squared, let's call it E incident, because there is nothing to scatter the field. So the total field is just the incident field produced by the source, right. Then next is I will write k naught squared, because it's vacuum, EI is equal to j omega mu jz of r. Okay. These guys, this EI is also a function of r, I am just not writing it over here. Okay. So this is our equation in the absence of object. Now when I add the object, now let's add add the object. In this case it is V2. So what happens now? I will say the same operator remains similar. Okay, so del squared now E of R, okay, this was also R, plus, now what do I write over here? The permittivity of the medium enters into this K term. So can I still write K naught? I cannot write, right? So I have to modify that. So it becomes the relative permittivity comes in over here. Okay. So when we had derived the wave equation, remember there was a epsilon, it was either we wrote it as KR or we can write it more precisely like this, okay, and ER. What about the right hand side, does it change? No, right, the current source is still there. Okay. In V2 it is 0. So even this J is a function of R. So in V2 the current source is 0. So wherever you are asked to evaluate this, so take a value of R, let us say R is in V1, then what will happen? Then the relative permittivity will be 1, that relative permittivity of vacuum is 1 and current source is present. I evaluate, take R inside V2, what will happen? I will have relative permittivity to be different from 1 and current source will be 0. Right. So both are functions of R now, it is the most general thing. The good thing is I do not have to specially say this is valid for region 1, this is valid for region 2, it is a general equation. Okay. So typically I do not know the current source and I do not want to get into the details of how the current is flowing in some antenna somewhere, right. So what can I do with these two equations to get rid of current source? Subtract, right. So if I do that, what do I get is, so del squared ER minus EI, that is common, okay. Then I have a K naught squared epsilon R ER minus K naught squared EI is equal to 0. So this is an equation which has it has pretty much everything we want. It has the incident field, it has the object information, and it has the variable that I want to find out, that I want to solve for. It has everything, and I have eliminated this current source. Actually the influence of the current source has been absorbed into the problem. In which term? The influence of the current source has made its appearance in the incident field, right. So it is not that I have completely removed the current source. So this is the equation that we have. Now can we solve this equation using what we already know, which is the Green's function over here? Can I use this? What do you think? So in order to use this Green's function over here, I should have another equation of the form what? Of the same form. Correct. Does the left hand side look like that of the of this equation over here, equation 3? Okay. So E minus EI, that I can think of as phi, right. But what about the second term, the term that accompanies K naught squared, is it in that form yet? It is not, right. So I can't immediately use this equation 4 to solve equation 3, but does it look impossible to do? No, right? There is just some simple manipulation that I have to do.